IR, NMR, UV, they are very important, but this mass spectrophotometry is very important as far as the analytical method is concerned, because this gives a information regarding its structure and molecular weight, whereas the other methods, they are just the indicative of the various groups present to the various compounds. So, here we get the atomic and molecular composition as well as the chemical structures. Now, it has four distinct advantages over the other methods. First is it is more sensitive than other methods, because here we use the mass over charge ratio. It has the maximum excellent specificity, which is determined by this fragmentation pattern. Every fragmentation pattern of the any compound, it is distinctive of itself. No other compound gives that type of a fragmentation pattern. Third, it gives the molecular weight. So, and the fourth one is it gives regarding the various isotopic abundances of the elements. For example, if chlorine and bromine is present in a compound, so it gives that how many two isotopes of the chlorine and bromine are present in that. Now, how it is made possible? A mass spectrum, it is obtained by converting the sample into the moving ions, and this is by bombardment of the electrons or other methods. The utility of this mass spectrometry is from the fact that it produces the family of positive particles whose mass distribution is characteristics of a particular compound. The mass spectral data, it is more easier to interpret as compared to the IR and the NMR. They are all of indicative, but this is exact information. So, it provides the information of the molecular mass. Accurate, it gives the actual measure of molecular weight. So, mass spectra can also be used for the quantitative analysis, because the magnitude of the ion currents at various mass settings, it is this is directly proportional to the concentration. The first true analytical application of the mass spectrometry was described in 1940, when at that time the focus was on quantitative determination, but in 1960 the focus is starting towards the identification, that is the qualitative one, and the structural analysis of the various compounds. Now, these are the general uses. They are used for to identify the organic compounds by virtue of this fragmentation pattern, determination of the molecular weight, the quantitation of the organic compounds at a low level, elucidation of the structural features of the unknown sample, determination of the isotopic incorporation of a stable isotope, and estimation of the elemental composition based on the appearance and multiplicity of the isotope peaks. Now, its common applications, they are used to identify the common environmental contaminants, to identify the drug and drug metabolites, the verification and confirmation of the product and product of organic synthesis, and the tracer studies, that is the incorporation of stable isotope labeled tracer compound into the biological pool of the hormones or chemical transmitters. Now, what is the basis? The basis behind this is ionization, the ionization of the sample compounds and the fragmentation, and this is made possible by either by the electron bombardment, chemical ionization, field ionization, or fast atom bombardment. The analysis of a range of the mass fragmentations are produced, and elemental composition of non-volatile materials, they are made possible by the RF spark. Next is instrumentation. Now, in the instrumentation design, functionally it has 7 components. First is inlet sample system, that is from where the sample is introduced. Second is ion source, that means how the compounds of the sample they are made into ions. Third, ion acceleration system. Once the ions are found, they are accelerated under the electric fields. And then fourth, analyzer. Once they got the velocities, they are then entrapped by the analyzer and produces the result. And fifth, ion collection system, which is then synchronized with the data handling system, which is normally a computer. And seventh, which is most important, that is the vacuum, which is connected to the components of 1 to 5. A very small pressure is required, so that the ions they have a collision free path. They must not collide with other ions, and that is why the pressure in the spectrometer must be less than 10 to the raised power minus 6 torr. Now, this is the diagrammatic diagram of the diagrammatic scheme of the mass spectrometer. Here the sample is introduced into the inlet system. It is then put into the ion source. Here by doing different methods, they are made to converted into the ions. Here it is then accelerated, then it is put to the mass analyzer, which is then to the ion collection system in the form of results, and these results are then synchronized with the data handling system, which is a computer. Now, its operation is based on the following sequences. First, a small molecule or small micromole sample is volatilized and allowed to leak into the ionization chamber, which is maintained at a pressure of 10 to the raised power minus 5 torr. Then these molecules are turned into the ions. They are either directly or indirectly by a stream of electrons from the heated filament towards the anode. The positive and negative charge are formed, but we have most important is the positive charge. We stop the negative ions and accelerates the positive ion. Then the positive ions are separated, the negative by a small negative potential on the slit, and then accelerated by a potential of few hundred to few thousand volts between A and B slit, which will be shown into the diagram in the next style. Then a collimated beam of the positive ions enters the separation area through the slit B. In the analyzer tube, which is maintained at a very low pressure, the fast moving particles are subjected to the strong magnetic field, which causes them to describe a curved path, because this is under the magnetic field, the radius of which depends upon the velocity and mass as well as the field strength. The particles of the different mass can be focused on the exit slit by varying the accelerating potential or field strength. Then the fifth sequence is the ions passing through the exit slit falls on the collector electrode, which produces the ion currents, which gives the results, which are then amplified and recorded as a function of field strength and accelerating potential. Now, this is the actual mass spectrometer. Now, this is the vacuum which is maintained in this whole instrument, and this is the sample reservoir from which the sample is introduced at a very small pressure, and then it goes into the inlet. Here it is the anode and cathode, from where the electrons, bombardment of the electrons are put on this sample. They get ionized. The negative ions are retained by the slit, but the positive ions are accelerated through these two slits, and then it gets entered into the field free drift tube, and this is under the magnetic field, and due to this magnetic field it takes the curved path, and ultimately it goes to the ion collector here, which gives the ion current, and this current is then amplified and it is given in a recorder. And this is the metal analyzer tube, and whole of this assembly, this is put under a very small pressure, that is 10 to the power minus 5 torr. The sample handling system, what is the purpose behind this is, it is to introduce a representative sample of a material to be into the ion source as a gas. The solid cannot be introduced, it should be in a volatilized form and under the low and reproducible pressure. The nature of the inlet system, and this is dependent upon the physical state of the sample. Now, this is the batch inlet. This is most commonly the sample is introduced as a gas, and the pressure of the sample in the reservoir is about 1 to 2 orders more or greater than the ionization chamber, and so that the steady flow of these ions or sample is into the chamber. The liquids boiling below the 150 degree centigrade, the suitable quantity can be evaporated into evacuated reservoir at a room temperature, and for the less volatile samples, the sample which are thermally stable, they are introduced directly into the ionization chamber, and procedure that requires the special equipment. The gaseous samples are readily handled by expansion of a small volume into the reservoir. Then the direct probe inlet. This is for the non-volatile and thermally unstable material. Here the sample is introduced through the sample probe, which is inserted into the vacuum lock. The probe consists of a holder and a small capillary tube or a cup that contains a small amount of sample. The principal advantage of the probe is minute quantity of the sample. This probe is equipped with a heater to volatilize the sample at a low pressure of the ion source. So, this makes the possible for the estimation of the carbohydrates, steroids and polymeric substances. Now, this is the recent one, that is the gas chromatography inlet system. That means the exit of the gas chromatograph will be the inlet for the mass spectrometer. Here in the gas chromatography, through the gas chromatography, various components of the mixture, they are separated and they are fed into the mass spectrometer. So, this causes the enhanced sensitivity by separating the sample components. So, this separation is done by the gas chromatography, that is through the tube of a porous glass or a Teflon, which is permeable to helium, but not to the larger sample molecules. So, this becomes the most useful tool for analyzing the complex mixtures. Now, this is the ionization chamber. This is the sample system from which the sample is introduced. It is introduced in this bombardment of the electrons. They are turned into the ions. The positive ions goes through the slit, whereas the negative, they gets repelled and retained by the slit. They are further accelerated between these two slits, and ultimately they are focused through this slit and enters into the tube, which goes through the magnetic field. So, this is a typical ionization chamber. Now, various methods of entrance or ionization formation. The most common is the electron impact source. How the positive ions are produced? They are produced by the electron impact, and they are first accelerated plate by a small potential difference between the plate and the repeller, and high potential difference potential between the first and second accelerators gives the particles their final velocities. And the third slit, it causes the collimation, that is the most of the ions they are moving in a parallel pathways to the beam, and in most spectrometers, potential impressed between the accelerator cells provides the mean whereby the particles of the particular mass are focused on the collector. Now, here the energy required to remove the electron from an atom is called ionization potential. Most organic compounds, it has 8 to 15 electron volt ionization potential, but the bombarding electron stream must have the 50 to 70 electron volt to give high efficiency of these ions. Only this much amount of energy produces the ions in a effective manner. Then the chemical ionizations. Now here the ions are not produced by the electron impact, but here the reagent gas, that is the methane, is introduced into the modified electron source. These methane molecules, they are first made into the ions, and these ions then bombarded on the sample molecules and causes the ionization of the sample. So this is largely a consequence of the collision with the reagent ions, not with the electrons. Now this is the example. The methane, when it gets bombarded with electron, it forms this molecule or this species, which is a strong proton donor, and when it combines with the sample, it forms the ion. This is the M+1 molecular ion. So it forms the methane. So MH is the analyte and MH1 is its M+1 ion. So generally this chemical ionization source causes less fragmentation, because in this case bond rupture is not so prevalent and leads to the simpler and easily interpretable mass spectra. Then the spark source. Now this is for the non-volatile inorganic samples like metals, semiconductors and minerals. Now here the radio frequency spark source is employed, in which both the electrons they are sample, or sample is ingrained with the graphite in the electron. So the radio frequency voltage of 30 kV is applied across the electrons, whereby the sample vaporizes to the gaseous ionic plasma. The ions in the plasma are then accelerated to the analyzer by a suitable DC potential. Then the field ionization source, in which metallic anode in the form of a sharp blade, which has an array of 1000 points spaced on 20 micrometer apart. It is and a cathode which serve as a slit, and the anode and cathode, they are located 0.5 to 2 mm apart, whereas the potential of 5 to 20 kV is applied, and gas phase in contact with the fine electrodes is subjected to the electric force, which is as large as 10 to the raised power 8 volt per centimeter. So this causes the ionization of organic compounds. The field ionization is a gentle technique, so the fragmentation is minimized. We get the molecular ion peak, that is M+1 ion, are often major products. So in a mass spectrometer, it is normally advantageous to get the two mass spectrum. One is to be obtained from the field ionization or chemical ionization. Second should be from the electron impact source, because from field and chemical ionization, it is the distinct indicative of this molecular weight, whereas the electron impact source, this gives a particular fragmentation pattern which tells about the nature of the compound. So both the spectra are important. Then the mass analyzer. The function of a mass analyzer is to separate the ions produced in the ion source according to their different mass and charge ratio. The analyzer section is continuously pumped to a very low vacuum, so that the ions may be passed through without colliding with the gas molecules. Single focusing analyzer with the magnetic deflection. When separators of this kind employ a circular path which is of 180, 90 to 60 degree, the path described by any particle represents a balance between the two forces. One is magnetic centripetal force, which is Fm. It is given by HeV. H is the magnetic field strength, V is the particle velocity, and E is the charge on the ion. And the balancing centrifugal force, which is Fc, and it is given by Fc is equal to mv square over r, whereas m is the particle mass and r is the radius of curvature. So, the kinetic energy of the particle, it is given at any time E is equal to E v or half m v square. So, v is the accelerating voltage applied in the ionization chamber. Note that all these particles have same charges regardless of the mass, are assumed to acquire the same kinetic energy during the acceleration of the electric field. But this is not the case, because this is only the assumption, because most of the particles, they have different speeds and different energies. So, particle must fulfill the condition that F m must be equal to F c. So, we equate that and we get, substituting both these equations, m over E, that is the mass over charge ratio, it becomes h square r square over 2 v, whereas h and r, they are constants. So, only this is the variable. So, by changing this, we can change the speed of this mass over charge ratio. So, the most particles possess the single unit of positive charge, thus any desired mass can be focused on the exit slit by a suitable adjustment of voltage. So, by simple changing the voltage, we can direct that particle to the focused exit slit. Then the double focusing analyzer. Now, this requires, it is the same as that of the single focusing, but here there are two focusings. One is electrostatic field, which makes this curved path, and second is magnetic field. So, it is made to pass through the first slit and second slit, and ultimately it again gets curved. So, the magnetic field, it turns it into the curved path, and ultimately it goes to the detector. So, single focusing analyzer is only electrostatic field, but where in the double focusing, it is electrostatic field as well as the magnetic field. This increases the resolving power and causes the, if the single beam, single focusing analyzer is used, it broadens the ion beam. So, the loss of resolving power, but in double focusing, electrostatic field and focusing is also done by the magnetic separator, it increases the resolution power. Then the second type of a double focusing instrument, it employs the Matthews-Herzog geometry. Now, this is a geometry, is this one, that a ray of ions, they are made to pass through the electrostatic analyzer, through the electrostatic field, and ultimately this is the plane, and ultimately it is put under the magnetic field. Now, all the ions, they get a different path under this magnetic analyzer. So, they fall on the different portions of this plane. So, this also gives a photographic depiction of this ion. So, this geometry is called Matthews-Herzog type geometry. It results in all ions of various mass to charge ratios being focused on the single focal plane, and is particularly useful for the photographic detection. The dispersion along the focal plane is linear with respect to the mass to charge ratio. Thus, identification of the lines is readily accomplished, and if the mass of the particles responsible for two lines can be determined. Then the time of flight analyzer. Now, this is the another type of instrument. Here the positive ions are produced intermittently, that means they are not produced continuously, but they intermittently by the bombardment of brief pulses of electrons. So, these pulses are controlled by a frequency of 10,000 hertz and a lifetime of 0.25 microseconds. The ions produced are then accelerated by the electric field pulse, which has the same frequency as but lags behind the ionization pulse. The accelerated particles pass through the field drift tube about a meter in length, and all particles entering the tube have the same kinetic energy. Now, this is the significance. Here all the particles, they are entering with the same kinetic energies, thus their velocity in the drift must be vary inversely with their masses. That means, the lighter particles, they are arriving at the collector earlier, and the heavier ones, they are coming later. Now, this is the schematic diagram of time of flight mass spectrometer. Here at one time electrons are bombarded, ions are formed, they are made to pass through slit, and heavier ones they are slower and the lighter ones they are fast. So, they reach there initially early and heavier they are coming late. So, whenever the lighter ions comes, they immediately response is multiplied and it is recorded. So, this is again the synchronization of the pulses. The horizontal sweep is synchronized with the accelerated pulses. But these time of flight mass separators, they have the less satisfactory results. The advantages is that ready insertion of non-volatile and heat sensitive samples. Second, instantaneous display feature. This is another benefit in the short lived species. So, they are smaller, more mobile and more convenient to use. Then the quadrupole analyzer. Now, if you see this, there are 4 rods which are put in the path of these ions. Now, here one pair of the rods they are given the positive side of the DC source and other pair is given in the negative terminal, and they are also fed the radio frequency AC potential to both the pairs. The combined fields they causes the particles to oscillate, they do not accelerate, but they causes the now the ions they gets oscillated while moving. So, during oscillation only a certain mass to charge ratio can pass through the array without removed by the collision with any of the rods. The mass scanning is achieved by varying the frequency and AC supply and varying the potential of the two sources while keeping the ratio constant. Quadrupole instruments are compact, less expensive and magnetic focusing is from the magnetic focusing instruments, but resolution is lower. Then the measurement of the ion currents. Once the ion currents are formed, they are currents, they are produced, they are passed through the large resistor to the ground, resulting potential drop is impressed on the field effect transistor or the grid of the electrometer tube. The resulting current is then further amplified before being recorded. Alternatively, they are used through the electron emission, that is the photomultiplier tubes, and the ion currents are ordinarily small, that is of the range of 10 to the raised power minus 7 to 10 to the raised power minus 9 ampere, which is equal to the 60 ions reaching the detector per second. In order to record the peaks of such diverse size, most mass spectrometers are equipped with several pens and each responding to the different current range. So, they separate pens they are giving the different peaks, and some instruments they have the set of mirrored galvanometers and they have different sensitivity. So, they give different readings with the different mass and charge ions. Then the computerized mass spectrophotometers, these are used the interface between the mass spectrometer and the computer. This is has a provision for the digitizing the amplified ion current signal plus the several other signals that are used for the control of instrument variables such as temperature, accelerating voltage, scan rate, magnetic field strength. First, the peaks must be normalized. The height of the each peak is relative to the reference peak is calculated. Often the largest peak is given as a taken as a reference, which is hypothetically given the number 100 or 1000. Each peak must be assigned a mass number. Then the assignment is frequently made on the basis of time of appearance and the scan rate. The periodic calibration is required. For higher resolution work, the standard must be admitted along with the sample. The computer is then programmed to recognize and employ the peaks of the standard as references for the mass measurement. For the low resolution instruments, the calibration must generally be obtained separately from the sample. So, the sample standard is not sent along with the sample because of the likelihood of the peak overlap. With the quadruple spectrometers, the mass of the ion reaching the detector is proportional to the AC voltage applied to the rods. Hence, a rod signal can be digitized and superimposed on the ion current signal. The computer is then programmed to employ the resulting signal for assigned mass. But for the magnetic instruments, a Hall probe is taken, which measures the magnetic field strength and can serve to provide the mass data. The computer output is then displayed both in a digital as well as graphically.